Hello everybody, welcome to Chemical Dada. So in this video we will discuss a very important question of the Benz rule. This question has still not been asked in any exam so far, but we can call this the AYQ if not the PYQ. AYQ meaning आने वाले year के questions. So we can call this the AYQ and let's see what the AYQ holds for us. It's a very interesting question though. It is like the CH3 radical fighting up against the CF3 radical. Now, this radical is sp2 hybridized, is planar. However, this radical is sp3 hybridized and is tetrahedral, or we can call it pyramidal. And the thing is, why so? Why are both the species different? Why are both of them different? Because both have got a carbon atom which are tri-coordinated and both are radical species. Then why do we call these different? One being sp2 planar and the other one being sp3 tetrahedral. Let's see now. Let's see how these species were formed at the very first place. Let's look at the CH3 radical. Now this molecule was initially something like this. There's a bond between A and this. Then you break the bond homogeneously and you get the CF3. Sorry, CH3. I did it, and you get the CH3 radical. Similarly, for the CF3 radical, you had something like this down the corner with two electrons here. You break the bond homogeneously, and again you get some CF3 species. Let's just make it a bit more readable now. CH3. Fine. Okay. Now, how are these formed? Let's look at the bonding structure of these. For the beginning, say, look at CF3A. We had initially something like this. This is very easy though. We have already done this in the previous classes. How to draw these structures. A. And then you do something very simple. You just break the bond homogeneously. You remove this electron coming from A and you make it something like this. Something like this. And we have one electron here. Now the question remains, this species was sp3. Now what about this one? Is this going to be sp2 or sp3? What is going to be the fate of this? It all depends on this electron. If we keep this electron in a pure p orbital, then it's going to be sp2, otherwise it's going to be sp3. Let's look at it how. We had a carbon, we now have a fluorine. Let's write like this. We have a fluorine here, we have a fluorine here, we have a fluorine here, and another lone pair in this manner. Fine. Now this is the sp3 hybridized case, where all the carbon bonds are sp3 hybridized. Like this is an sp3 hybridized orbital forming the bond, so is this one, and so is this one. And this electron, this odd electron, as we call it, the odd electron species, this odd electron is kept in, sorry, it's going to be one electron, not two. This odd electron is kept in a sp3 hybridized orbital. Remember it. It is kept in a sp3 hybridized orbital. Also, it can be something like this. The carbon can be here, one fluorine this side, one fluorine this side above the plane, and one fluorine like here. And like these are sp2 hybridized orbitals, sp2, 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 and you have a pure p orbital stationing only the odd electron. And this, on the contrary, instead of being an sp3 hybrid orbital, this is a pure p orbital. Understood? This is a pure p orbital. Fine. Okay. Now the matter of fact is, which one is more stable? Is it the sp2 form or the sp3 form? The question lies in the Benz rule. What did we learn in the Benz rule? The Benz rule taught us very clearly that the electronegative substituent always prefers an orbital having high p character and low percentage s character. And the reason has clearly been explained in the previous video. For those of you who are still not aware of this, please get back to the previous video, watch it, and then come back to this again. Now, in this case, the sp3 case, there is like 75% p and some 25% s. And in the sp2 case, we have 66% of p and 33% of s. Now, fluorine, as we know, fluorine being the highest electronegative element, the highest electronegative element in the periodic table, it will always prefer an orbital having higher p nature in order to be stable. In order to be stable. Understood? It's already discussed in the previous video. So since fluorine prefers a higher p nature in its bonding orbital, so it will obviously prefer the one with the sp3 hybridization having 75% p. So this is going to be CF3. So CF3 will be CF3 will be tetrahedral or pyramidal having a sp3 structure, hybridization structure. Understood now? Now for CH3 radical, I think guys have already got the answer so far. So some of you must have. So it is like this. Uh, CH3A. It initially was like this. It initially was like this, where you had three hydrogens and one A attached to it. Then you just remove one A from this. You just remove one A from this, and you get our desired radical, what we have been studying so far, like this species, this radical. So okay, one more thing. This was sp3 hybridized, as you already know. And what about this now? It can either be sp2 or it can be sp3, as we already discussed in the previous case, in case of CH3 radical. Like if the odd electron, let's draw it in this manner, the odd electron, if the odd electron is kept in a pure p orbital, you get sp2, and if it is kept in a hybridized orbital, as it already was in this bonded species, see, in this bonded nature where A was already there, this electron was kept in a hybrid orbital. Now you have two choices. You can either continue to keep the electron in the hybrid orbital and keep it sp3 like before, or you can shift it to a pure p orbital and change the entire molecule to sp2. Now what does carbon do? Now guys, remember one thing. Initially carbon was like this. After you excite the electrons, obviously was like this. You have 1s and 3p. So these were separate orbitals. You come and then you mix them up, you mix them up, you mix them up, you mix them up, and you make the sp3 orbitals. And in order to mix them, you need energy. In order to mix them up, you need energy. Now remember one thing, nobody does anything for free. Carbon is spending energy to mix up the orbitals to form the sp3 hybrid orbitals because they form stable and stronger bonds. Understood? And in this process, they release energy. They release more energy. Understood? Like to mix them up, to mix them up, say for example, you are spending energy worth 20 units, and when you form the bonds, you release energy, say like 35 units, 35 units. So overall, it's making the system more stable, more stable. Now moving on to CH3 dot, moving on to CH3 dot, this species, this species, this species, this electron is there. Now, this electron initially was used in bond formation. See, this electron was used in bond formation. So carbon was having a finite profit by hybridizing this orbital. Carbon was hybridizing this orbital and was getting a finite profit by forming a bond. Now in this case, this electron does not form a bond. It does not form a bond. So even if carbon spends say 20 units of energy, 20 units of watt energy to mix them up and keep this electron and keep this electron in an sp3 hybrid orbital, what will the carbon gain back? What will the carbon gain back? Nothing. It will only spend the energy to mix things up and keep it in an sp3 orbital. But at the end of the story, it is gaining nothing because this electron is not forming bond. It's not forming bonds. So carbon prefers, okay, since this electron you are of no use to me, I will keep you in a pure p orbital. So carbon prefers to keep the odd electron in a pure p orbital. Understood? In a pure p orbital. So it looks something like this. Looks something like this, with a pure p orbital storing one electron, odd electron, one odd electron in a pure p atomic orbital. Understood, guys, why this thing is sp2 hybridized, whereas CF3 dot is sp3 hybridized. And also hydrogen being the substituent, it has got a very low electronegativity and it has got no special love for p like fluorine has. Like we have already seen that fluorine has a very soft corner for the p orbital because it is highly electronegative and prefers a p orbital to form a bond with. However, hydrogen has got no such special affection for the p orbital, and also it does not mind forming a bond with this orbital, so forms a bond with the s orbital itself, forms bond with s only, understood, with s only. So carbon does not spend any extra energy to keep the electron in an sp3 orbital, so it houses the electron, the odd electron, in a pure p orbital, and then does not and is saved from spending any extra energy, and it brings stability to the system. And so it is ch3 dot is sp2 hybridized and has a planar system, has a planar system, has a planar system. Understood? Whereas CF3 dot is sp3 hybridized and has got a tetrahedral or a pyramidal structure. So that's all for today. I hope you enjoyed this new question. I hope you enjoyed the AYQ, as I call it. You enjoyed the concept, you enjoyed the question. So for now, that's it. We'll meet again in some next video. So happy learning. Bye.